To evaluate an integral, we must find the antiderivative of the function that's in the integrand. Now, to this point, we've looked at some pretty basic antiderivatives using power rule, basic trig functions, exponential, logarithms. But what if we come across a situation where we have to evaluate an integral that shows composition? If we take the perspective that this function that's in the integrand position was the result of a differentiation upon some other function, which would represent our antiderivative, recognizing the composition would indicate that a chain rule was applied. So as a review of what the chain rule is through the differentiation process, let's see if we can come up with a rule to reverse that chain rule. So we know if we have function composition, to take the derivative, we do derivative of the outer, compose with the inner, times the derivative of the inner. In the event that we have to integrate a function that has composition, we can reverse that differentiation process by first dividing by, or at some point I should say, dividing by the derivative of the inner, taking the antiderivative of the outer still composed with the inner, and then don't forget that plus c for the constant of integration because we have an indefinite integral. So this is how we can reverse the chain rule when we recognize composition. Now let's just look at a very basic example where this could be applied. So let's say we have the integral of sine of 4x dx. If we ignore the composition, and we just took the antiderivative of sine, which is negative cosine, recall that our antiderivative should be a function where if I take the derivative of that, I get the function that's in that integral. When I take the derivative of that function, I would need to use a chain rule. In taking the derivative, we will get positive sine of 4x times 4. Now, in the integral, there is no times 4. So how do we account for that that should be there? That's where that dividing by the derivative of the inner function comes into play. So recognizing the composition will allow us to implement that additional step that's needed to fully reverse that chain rule application. So our final evaluation should show negative cosine of 4x, so antiderivative of the outer, still composed with the inner, but dividing by the derivative of the inner. Reformatting, we'll get negative 1/4 cosine of 4x plus c. So there's my antiderivative, and if you were to take the derivative of that, you would get sine of 4x. Now, there are situations where recognizing the composition is easy, but finding or reversing the chain rule is difficult. Or there are some instances where even recognizing the composition can be challenging. So can we use another method that will help us out when trying to evaluate an integral that had a chain rule applied? And the answer is we're going to use what's called U substitution. And the thing to keep in mind is that U substitution, it reverses the chain rule, but not quite in the same way that we're doing here. It's really that method in disguise. But the ultimate goal of the U substitution is to reformat our integral into something that is much easier to anti-differentiate. And you'll see what I mean when we go through some examples. But let's first introduce the process. So knowing that U substitution's goal is to reverse the chain rule, let's imagine that the chain rule, for some form of it, we'll do the actual chain rule. I think that will best illustrate what's going on. So imagine the chain rule is inside our integral, and we want to reverse that. To use U substitution, what we can do is set U equal to some function. The function we want to choose in this case is the function that is composed within the f prime. So we're going to take U to be g of x. And we'll go into more detail in a second on how we can recognize what to set U equal to. But once we've decided what U equals, we take the derivative of U. Now we're making a substitution here. So that g of x we have redefined as U. So I'm going to make that substitution times g prime. Now, if I'm going to redefine the variable of integration to be u instead of x, I need the differential to match. So having a dx differential is not going to work here. I need a du to correctly evaluate the integral. So what we can do is by taking the derivative of u, which is what we did in the second line, it allows me to solve for dx. That's why we want to take the derivative of that function. And solving for dx, we'll find that du divided by g prime of x equals dx. And I can make the substitution for dx, which is du over g prime of x. Now, to correctly evaluate this integral, we strictly want our function to now be in terms of this new variable of integration, u. I still have some x's, but we'll notice that these g primes cancel. So we have this as a result. From where we started to where we are now, you can see there's a drastic difference in a much more compact, easier to deal with function. Anti-differentiating f prime will just get us f. So f of u plus c. However, the original evaluation required to integrate with respect to x. So my final answer should be with respect to x. So all we have to do is back substitute that u, which we defined to be g of x. And here is our antiderivative, f of g of x plus c. Now, if we take the derivative of this, we know the derivative of that is represented by that chain rule notation. So that is in fact the correct antiderivative, and this process worked. So u substitution's goal is to reformat the integral to make the anti-differentiation process easier. So now, what are we looking for to know when to use this thing? So with u substitution, we want to recognize composition and or a product that is related through differentiation. And once we think we're looking at function composition or a product of two functions that look to be related through differentiation, there's a good chance that u substitution can help you evaluate the integral. Now, if we have a product of two functions that are unrelated through differentiation, another technique is likely necessary. So let's stick to products that are related through differentiation to illustrate how to use u substitution. Once we have identified that we think u substitution is needed, the question is, what do we set u equal to? We're going to look at two different scenarios. So the first one, when you look at the function, set u equal to the inner part of what we're going to call the ugliest piece of the function. So determine, of the pieces that you have that form this function in the integral, which one's the ugliest, or which one's the most complex? Set u equal to what's inside of that, so the thing that's composing. Okay, so that inner part, function composing that term. Okay, that's a very good place to start. Now, it may be difficult to recognize in some cases because it could seem like these two pieces that are being multiplied together that we think we need a u substitution for, we can't decide which one's uglier than the other. They look pretty much the same to us. So if this doesn't work, or it's difficult to identify what to set u equal to based on this first recommendation, the second thing you can look to do is set u equal to the part of the product that is the antiderivative of the other piece. So those are the two things I would look out for. then again, you know your U substitution is successful. So you may question, did I set U equal to the correct function? Your U substitution is successful if you can redefine the integral solely in terms of U du. Now, you don't always want to look to just do that reverse chain rule application like we did with the original example from this video. And the reason being is if you get to different techniques down the road, knowing how to utilize a substitution method to simplify the integral is going to be a really nice tool to have. So we want to get used to using this U substitution. So now that we have it introduced, let's apply it. Here's our first example. We look at this integral, and on initial observation, you may say that this thing doesn't appear to have an antiderivative that is in that simple form like the ones we've been dealing with thus far. But what we will notice is that we have a product of two terms, x and cosine of 2x squared. We have a composition here, and we have two terms that look related through differentiation. What do I mean by that when I was saying that before? Well, x and 2x squared, if I differentiate 2x squared, there's an x involved in that. It's not exactly x, but they're related, okay? So that's what I mean by that. They're not going to be perfectly antiderivatives of each other or derivatives of the other, but rather there's some relationship there. So we think U substitution is going to be a useful tool here. The question is, which piece do I set U equal to? A good place to start, set U equal to what's inside the uglier of the two parts of this product. So I have x and cosine of 2x squared. Hopefully you would agree that cosine of 2x squared is much more involved and uglier in terms of the way it looks. So let's say U we think should equal 2x squared. If that's the case, we're going to take the derivative of U in order to replace the differential so that it matches with my substitution. We'll solve for dx. And now let's make our substitution. So we have the integral x cosine, and we're going to replace 2x squared with u, and we're going to replace dx with du over 4x. I still have x's here, so my integral is not solely in terms of u du, but what you should notice is these x's cancel, and now we have the integral of 1/4 cosine u du. I can pull out that 1/4, and we now see that our original integral has been redefined to be strictly the function cosine of u, which is a lot like the functions we were taking antiderivatives of before. So we've reformatted this thing so it's a much easier evaluation. So what's the antiderivative of cosine in terms of u? It's going to be sine u, and then plus c because we're evaluating an indefinite integral, so don't forget that constant of integration. However, the last step, and a necessary step, the original problem is asking us to integrate with respect to x. So our answer should be a function in terms of x. So let's just back substitute. What we set u equal to. There is our final answer. So we used u substitution successfully to evaluate the integral. Now, going back to reversing the chain rule. So do we need to use U substitution all the time? Not necessarily. Okay, so some people, again, are savvy enough to evaluate this right from the start. Now, if you're going to use the reverse chain rule, the first example I brought up didn't show a product. There was only one piece. So if I'm going to apply reverse chain rule when there is a product, what am I reversing the chain rule on? What piece? You're going to reverse the chain rule on the uglier piece. Okay, so if that's the case, to find the antiderivative of this, we are going to say that this should equal, we're going to have x antiderivative of the outer, there's going to be sine still composed with the inner, divided by the derivative of the inner, okay, plus c. So you're just going to antiderive that uglier piece if you're going to use the reversing chain rule idea instead of the U substitution. Now the x's cancel and we get the same exact answer as before. And you may say, well, why aren't we always doing that? That looks to be much easier. You did that in 2 lines as opposed to all that u substitution. Well, it's not always easy to identify how to reverse that chain rule. For instance, we may come across a function like this. Again, some people may be able to easily reverse the chain rule on this, but I think a u substitution is a better application here. I'm going to rewrite that dx off to the side because remember our integral format is some function times dx. So when I see in the numerator, I can just separate it if I'd like to make an easier identification of what function I'm dealing with. Now, technically, there's a product here. We have 1 over x times 1 over ln x. The products seem related because the derivative of ln x is 1 over x. So there's our relationship there where we think maybe a chain rule or a reversal of the chain rule can work. Now, I would prefer to use a u substitution here. And the question is, what do I set u equal to if I think that that is the method to use for evaluation? Well, of these two pieces, I think 1 over ln x would be considered uglier. But remember, I don't want to set u equal to the whole thing, but rather what's inside the whole thing. So what's the composition here? Well, think you have 1 over x, and we composed it with ln x. So the bottom here is the composition. So let's set this equal to ln x. Now, if you didn't recognize the composition, no worries, because the other method, the other technique I told you to look out for is I could set u equal to the piece that represents the antiderivative of the other part. So the antiderivative of 1 over x is ln x. So I'm setting u equal to that piece that looks to be the antiderivative of the other one. Now, when we differentiate the u function, we get 1 over x. And when we solve for dx, we get x du. So let's make our substitution. We're going to say that ln x is u. We're going to say that dx is x du. And we know if our u substitution was successful if the original variables for the integral have disappeared. So now, what I started with, 1 over x ln x, is then been reduced or reformatted to 1 over u du. And the antiderivative of 1 over u is ln, absolute value of u, plus c. Let's make sure that our final answer is in terms of the original variable of integration, which is x. So u we defined as ln x. So ln of ln x plus c is our antiderivative or evaluation for that indefinite integral. This next example is a tricky one. When you first look at this, tangent x seems very basic. The only issue is finding the antiderivative of tangent x is not so simple. Finding the derivative of it is secant squared. We know that from our differentiation chapter. So what can we do with this? Because it looks awfully innocent upon the first observation, but finding the antiderivative, I don't know of an antiderivative right off the top of my head that gives me tangent x. So let's change tangent x to the ratio of sine and cosine, which we know to be equivalent. Now what we have here is a product, right? We have 1 over cosine times sine. And they are related through differentiation. We know the derivative of sine is cosine. The derivative of cosine is negative sine. So can we use a u substitution? Because it looks like we have a product related through differentiation. So it's not clear that there's a composition necessarily, unless you separate. And you may say, okay, now I recognize there's a composition with this rational function here, and the composition is cosine x. So based on the recommendation we brought up before, let's try to set u equal to what's inside the uglier piece. And I think the uglier of the two would be 1 over cosine. If we differentiate, we're going to get negative sine. And if we solve for dx, we're going to get this. So we're going to get 1 over u sine x du over negative sine x. Now, we know we were successful because these signs cancel, and we get negative 1 over u du. We can pull this negative out to the front if we prefer. And then upon the evaluation of this indefinite integral, we're going to get natural log of u plus c, that negative. Let's make sure our answer is in terms of the original variable of integration, So let's plug in cosine x for u, and there is the antiderivative of tangent. So that's not something that I think I would remember off the top of my head. But reformatting the function using a u substitution made the original integral that I was working with much easier to deal with. Knowing the antiderivative of 1 over u is something we should know off the top of our head. Quick, easy. We know it's ln, absolute value u. Make the back substitution, and there is your answer. So there's a u substitution in disguise. So look to reformat equations in the event that you're not necessarily aware of what the antiderivative of something that looks awfully innocent like tangent x would be. Now, a couple more examples to finish out the video, because we're going to look at definite integrals and how it relates, or what changes we need to make when we use a u substitution. Here, we notice we have a product. The product looks related in the sense that r is involved in the derivative of r squared. We also see there's a clear composition underneath the square root. So maybe u substitution is what we need to evaluate the integral. Now again, there are other integration techniques out there, so u substitution isn't always the answer. But when those conditions are met, this is a good place to start. We want to set u equal to what's inside the uglier of the two pieces. We're going to differentiate u with respect to r, and we're going to get negative 2r. We'll get du is negative 2r. Sorry, du over negative 2r is equal to dr. Let's make our substitution. I'm not going to put the lower and upper limits of my integral in just yet, and you'll see why. We're going to substitute u in for what we defined u to be. We're going to replace dr so that our differential matches the variable of integration. We'll see our r's cancel, so we know our u substitution was successful. That negative 2, I'm going to pull out to the front, so we have a negative 1/2 out here, du. Now, if we are using a u substitution on a definite integral, so recall to evaluate, we're going to do antiderivative, which we haven't got yet. We've just reformatted using the u substitution. But then we must evaluate the antiderivative at the upper and lower bounds and find the difference between them. But if we're going to redefine the integral with a new variable, we also have to change our lower and upper bounds. And we change them by taking those values and evaluating the u function at those points. So we have to evaluate u when r is equal to 0 and evaluate u when r is equal to 1. So when it's equal to 0, we're going to get 1 minus 0 squared, which is 1. This is going to equal 1 minus 1 squared, which is 0. So I'm going to change the lower bound from a 0 to a 1 and the upper bound from a 1 to a 0. And again, those numbers came from me evaluating what I defined u as at the lower and upper limits that were originally presented to me. Now, when we take the antiderivative, so remember, we're going to have this negative 1/2 out front. The antiderivative, I would reformat that radical into a power function. So we're going to have 2/3 u to the 3/2. So add 1, divide by the new exponent, dividing by 3/2. So the same thing as multiplying by 2/3. That's where that comes from. If we want to distribute that negative 1/2 at this point, we're going to get negative 1/3, 3/2, and we're going to evaluate from 1 to 0. We don't have to flip the integral if we don't want to. The fundamental theorem of part 2, the evaluation part, is going to take care of the signs for us. So if you want to flip the integral so it goes from least to greatest as we work from bottom to up, or top of the integral, you can. Just remember, if you flip the integral, make this or change the sign up front. So that would become a positive 1/2 if you want to integrate from 0 to 1. Now we're going to evaluate this function at these points. So at the upper minus at the lower. This first one, 0 minus a negative 1/3. 0 minus negative 1/3 is positive 1/3. So there's our evaluation of the definite integral, where we had to change the lower and upper bounds because a u substitution was needed to find the antiderivative. Now, if you don't use u substitution and you just find the antiderivative from the start, then you don't need to change the bounds. So if we try to use that reverse chain, which we can do now, To use the reverse change, it may be best to reformat it like this. So if I'm going to use reverse chain idea, look at the uglier piece. Take the antiderivative of the uglier piece, and you're going to keep that r out there because we're only doing this on the uglier piece, and hopefully the r cancels, right? So it's going to be antiderivative, so add 1, and then we got to divide by the derivative of what's inside. We don't need a plus c because this is a definite integral. So cleaning this up, we're going to get negative 1/2, 1 minus r squared. My mistake, I forgot one thing. Backtrack. So we're going to do antiderivative of the uglier piece, which again, we're going to add 1, but I forgot to divide by the new exponent. So I'm going to divide by 3/2, but I also have to divide by the derivative of the inner. So it's going to be divided by 3/2 negative 2r. Okay, so I forgot to divide by that 3/2. So you add 1 and then divide by the new exponent. That's our power rule. So I forgot that. Now clean this up. On the bottom here, we're going to have negative 3r. R's cancel. And we're going to have negative 1/3, 1 minus r squared to 3/2. This is our antiderivative. We're evaluating from 0 to 1, so I don't have to change the lower and upper bound because we are working with the original variables. We didn't use a u substitution. So when I plug in 1, that in the parentheses is going to go to 0, so the whole value is going to go to 0. If I plug in 0, it's going to be 1 to the 3/2, which is 1, so minus 1/3, so it's going to be minus 1/3, and we get that positive 1/3 again. Now, I don't know about you, but that arithmetic and that math and what you have to think about, I think that's more complex than just using the u substitution. So while the reversal of the chain rule is there for us to use, the u substitution makes the antiderivative process easier. You notice the first time around, I forgot to do dividing by that 3/2, right? So little things like that can screw everything up. So we want to use that u substitution to simplify the integral. Again, I can't stress out enough, that's the point. So last question. This one, it's actually not a bad idea to use the reverse chain, but let's use a u substitution here as well. There's not a product, but there's a composition. So let's set u equal to what's inside, and there's only one thing here. And if we differentiate, so here, there's no x's that cancel, but through the u substitution, they went away anyway. So we're going to have 1/2 on the outside, 1 over u du. Let's change the lower and upper bound. So if I plug in negative 2, I'm going to get negative 7. If I plug in 5, I'm going to get 7. Antiderivative of 1 over u is 1/2 ln of u evaluated from 7 to negative 7. Here, we're going to have 1/2 ln of 7 minus 1/2 ln, and therefore this would go to, go to 0. So remember with the ln, make sure you're taking the absolute value of that number that we plug in. So you'll see we have to evaluate that u at the negative 7 becomes a positive 7. So it's 1/2 ln 7 minus 1/2 ln 7. Okay? So remembering that absolute value is important for the absolute value. I did copy this example down wrong. It was supposed to be a positive 2, so I want to show you if it were a positive 2 and we use reverse chain, how would that work? So we have a composition here. What we can do is say that when we have 1 over something, I know that its antiderivative is ln, still composed, so we have a composition, right? So let's reverse the chain rule. So antiderivative of the outer. So the outer is 1 over that thing. So it's going to be ln of 2x minus 3. And then we have to divide by the derivative of the inner. Okay, so antiderivative of the outer, still composed with the inner, divided by the derivative of the inner. And we get that. Now this is evaluated, supposed to be from 2 to 5, but I copied it down wrong. So if we plug in 5, I'm going to get ln, or 1/2 ln of 7, minus 1/2 ln of, we plug in 2, we'll get 1. Okay, now ln of 1 is 0, so that whole thing goes away, and we just have 1/2 ln of 7. So there's an example of doing a problem like that. Sometimes when you have like 1 over some expression, using that reverse chain is not a bad idea. But when in doubt, I think the use substitution, although a few more steps, makes the anti-differentiation process much easier. There are several examples. Make sure you're changing your lower and upper limits if it's a definite integral to carry through on that fundamental theorem part 2. But there is your video on reverse chain and use substitution for evaluating integrals.